Okay, we're back for the next part of chapter 14, factor rings. Okay, so let R be a ring and A be an ideal. Then the factor ring definition. So again, it's kind of like the division notation that we use for factor groups. R mod A or R divided by A is, so as a set, it's the set of additive cosets of A. So things of the form R plus capital A, where R comes from the ring R. Again, A, the set A just appears there. Think of it basically as a label that's telling you what kind of object you're dealing with. Okay, so we'll look at some examples momentarily. But this is the set. The elements are things that look like this. So an element from the ring plus the set A. All right, then our operations, now we're dealing with rings, so we have addition and multiplication operations to define. So addition, if I have two things of this form, let's say R plus A and S plus A. So here's one element of the factor ring plus a second element, say S plus A. Then to define an addition operation, I have to tell you what this equals as one of these elements. So I have to get an element of this form. So it's going to have a plus A, but the new representative, the new element here is R plus S. Okay, so far, this would be exactly the factor group under addition. So remember, any ring is a group under addition. It's an abelian group under addition. So A would be a normal subgroup under addition. If I did this factor group, this would be the resulting operation. So far, this is all just factor group stuff applied to addition. We also have multiplication, however, in a ring. So if I have two of these things and I multiply, R plus A times S plus A, I need to get something times A, and it's just RS plus A. Okay. I don't want to spend too much time proving that this is well defined and everything, so let me just kind of give you a quick sketch of why this works. I'm going to not go into all the details, but I just want to kind of show you how it works. So I don't really need to justify the addition because that goes back to stuff we did with factor groups. But multiplication is new. Here's an informal explanation. Since we kind of skimmed on coset discussions, I don't want to get too involved here. But just the idea is this. If I treat this as a product of two binomials, just for simplicity, let's just think of it as if I was multiplying two binomials. So I FOIL this. R times S, R times the set A, plus the set A times S, plus A times A. Now, this doesn't quite make sense formally because we're multiplying elements times sets, but let's just think about what happens here. R times S is what we want to end up with. R times a set A, well, A is an ideal. So we can think of ideals as they will absorb any other element into themselves under multiplication. If I multiply something from the ideal by something that's not in the ideal, the result is in the ideal. So R times A is essentially just A. It absorbs the R into it. Same thing here. Multiplying the ideal by something on the right that's not in the ideal, that S gets absorbed into the A. So that's also an A. If I take two things from A, if I take two A's and multiply them, that's like I'm taking an element from the ideal and another element from the ideal. Their product will also be in the ideal. So that'll also be an A. But ideals are closed under addition, so if I add these A's together, that's just an A. Okay, so the right way of writing this out would be with representatives. So we well defined in this, we take two elements that have the same representative R. Sorry, let me say that again. We take two representatives of this coset, so two different R's that differ by an element of A, and two different S's that differ by an element of A, and you multiply them and show that you get RS plus an element of A. Okay, so it's similar to what we briefly did back in factor groups, but I want to think of it like this. A absorbs things under multiplication, and A's added together are just A. Okay, so let's look at some examples here. Hopefully it'll make more sense with some concrete examples. Okay, so let's do polynomial examples, since those are really the heart of ring theory. So let's look at ZX mod the ideal generated by X. So as a set, this consists of things of the form a polynomial plus this ideal. So f of x is just some polynomial in Zx. So that's it. It's an integer polynomial. Okay, so remember what x is, the ideal generated by x is. It's the set of polynomials with no constant coefficient. No constant term. So ideal generated by x is the set of polynomials with no constant term, with a zero constant term. Okay. So let me just write a couple examples and let's add and multiply stuff. All right, let's do an example of multiplication. Say 4x plus 1 plus the ideal times x squared minus 2 plus the ideal. Say that again. All right, so let me try this one more time. Let's do this a tedious way first, then I'll come back and do it a slightly faster way. So the definition of multiplying in a factor ring is I take the ring elements, the representatives for each coset, and I multiply them. So I'd have 4x plus 1 times x squared minus 2, and then I just tack on plus the ideal. Okay, so now this multiplication here, that's just occurring within the ring, within the polynomial ring Zx. So I multiply this out, that would be what, 4x cubed plus x squared minus 8x minus 2. So that is my outcome, but I can simplify this. Again, this ideal consists of every element with 0 constant term. So from my representative here, if I just pick everything other than the constant term, that all has x as a factor. So that part has x as a factor, so each one of these terms can be absorbed into the ideal. So this coset simplifies as -2 plus bracket x plus the ideal. It's just like integers mod in, so modding integers by in. You can reduce your number by subtracting multiples of n. Well, in this case, I can reduce my polynomial by subtracting multiples of x. So all these multiples of x, they don't really matter. They can be absorbed into this label here. Okay? So with that in mind, a more efficient way of doing this would have been to reduce first. So -2 plus x is my answer I'm supposed to get. Well, what happens is I could have just reduced these before I multiplied. 4x doesn't really matter, so I can absorb that into my ideal. I have 1 plus bracket x. X squared is a multiple of x, so it can be absorbed into the ideal. I have -2 plus the ideal. And now I have reduced cosets. 1 times -2 is -2. Right. So let's do another one. Let's do a slightly more complicated ideal. Let's do the factoring zx divided by the ideal generated by x squared. This means, since I'm dividing by x squared now, that means whenever I have a polynomial that involves a factor of x squared, so it has x squared as a factor, that can be absorbed into the ideal. So just let's do a reduction example first. If I have 5x to the 4th plus 3x cubed minus 9x squared plus 8x plus 4. And I want to reduce this. We'll just think of term by term. Or better yet, I can do it term by term, but here, the 5x to the 4th down in -9x squared, all of those I could pull out an x squared. So this polynomial here, that has x squared as a factor. That means that part lives in the ideal. 8x plus 4 doesn't live in the ideal. So it has to remain a part, but this part here doesn't matter. I can basically just ignore it. I can have that get sucked up into the ideal there and reduce my coset to just 8x plus 4 plus the ideal. Okay, so it reduces down to basically a linear polynomial is all I need. Okay. Okay, so let's look at how these multiply in general. In this ring, in this factoring, let's look how things multiply. Okay, so as we just saw with that example, any element here can be reduced down to a linear polynomial. So anything in this set could be written as, say, ax plus b plus the ideal. Right? I don't need anything beyond x because that could just be sucked up into the ideal. So here's one element. If I have a second one, cx plus d plus the ideal. Let's just see how these multiply in the most basic way. Right, so I would multiply this polynomial times this polynomial. That would give me acx squared plus adx plus bcx, so ad plus bcx plus b times d. So I just multiplied this times this with the FOIL method, and then I combine my like terms already. All right, so I'd get that, but how does this simplify? Well, once we get an x squared, that term doesn't matter anymore. The x squared term can be sucked up into the ideal, so I don't need that. My product simplifies to be AD plus BCX plus BD. Okay. Let's do this example. All right. Okay, so let's talk more about factor rings as they relate to different types of ideals. So if I do a factor ring using an ideal with a certain property, what does that tell me about the resulting factor ring? Okay, so let's do for these, let's assume that R is a commutative ring. Yeah. Let R be a commutative ring. It doesn't necessarily have to have a unity element for what I'm going to define here. A proper ideal A of R is called prime if it has the property that when A times B is an A, that implies one of the two elements is already an A. So either A or B is an A. Little a is in capital A or little b is in capital A. Okay, so proper ideal means it's just not the whole ring. So proper ideal is called prime if it has this property. So that basically elements of the ideal cannot be factored using elements that are not in the ideal, using only elements that are not in the ideal. If it's factors, then something in that factorization is already a part of the ideal. Okay, so let's look at some examples first. some prime ideals and some non-prime ideals. Okay, so example, start with the easy one. So 2z, the even integers, is a prime ideal in the integers. Because if a times b is even, then a times b contains a factor of 2. That 2 has to come from one of the two elements, at least one of the two elements. Okay, in other words, if neither of these was in 2z, if a was odd and b was odd, a times b would also be odd. So if a times b is in 2z, then a is in 2z or b is in 2z. Maybe both, but at least one of them has to be in 2z. Oops. I don't know what I'm doing there. The ideal generated by x is prime in zx. Okay, so remember one way we had of describing this ideal? It was the set of polynomials that for which 0 was a root. So, in other words, f of x times g of x is an element of this, means f of 0 times g of 0 equals 0. These are equivalent statements. So if f of 0 times g of 0 equals 0, then this is just an integer equation here. Both sides are integers. And integers are an integral domain, so 0 cannot be factored without one of the factors already being 0. If a product equals 0, one of the factors is 0. So this implies that f of 0 equals 0 or g of 0 equals 0. But that's equivalent to saying that one of these is already an element of the ideal. Okay, so that's prime. Let's look at an easy example that's not prime. Let's do two examples that aren't prime. What if I have 6z? Six z is not prime. It's not a prime ideal in z. Okay, it is an ideal. It's the ideal generated by 6. But it's not prime because I can find an element which factors as elements that are not in 6z. So that element would be 6. 6 is an element of 6z. 6 equals 2 times 3. And neither 2 nor 3 is an element of 6z. So neither 2 nor 3 is a multiple of 6. So 6 factors as a product of things that are not in the ideal. This is multiples of 6, the set of multiples of 6. So 6 is a multiple of 6, but it factors as a product of things that are not multiples of 6. Okay, so this example and the previous examples, or the 2z example, that kind of motivates the usage of the word prime for these ideals. In the integers, prime ideals are generated by prime numbers. Non-ideals that aren't prime are generated by non-prime numbers, like 6. Composite numbers like 6. All right, let's do a non-integer example. The ideal generated by x squared minus 1 is not a prime ideal in the polynomial ring Zx. So because x squared minus 1, that polynomial is certainly an element of this ideal. But it factors as x plus 1 times x minus 1. So it breaks down into a product of two simpler polynomials, neither one of which has x squared minus 1 as a factor. This ideal is the set of all polynomials that have x squared minus 1 as a factor. So if I factor it as this, neither one of these individually has x squared minus 1 as a factor. So it breaks down, and these individual polynomials are not elements of the ideal. Okay. So there's an example in a polynomial setting. All right, so if we have a prime ideal, now getting back to the point, if we form a factor ring using a prime ideal in the right context, let me be careful, we'll get a certain type of ring as our factor ring. So what we want to say is let R be a commutative ring with unity. And let A be an ideal I don't need to do it like this, but just for a little bit more clarity, let's just go ahead and assume A is proper. Let's specify this it is proper. Otherwise, we get into little subtleties and definitions I don't want to worry about. Then let's say it like this. So we have a proper ideal A, then R mod A, the factor ring, is an integral domain if and only if A is prime. So when we deal with prime ideals, the corresponding factor rings are integral domains, is the point. Okay, so let's prove this. Let me get the simple stuff out of the way first before we get into the meat of the proof. So let's just get this observation out of the way first. If R is a commutative ring with unity and A is proper, without worrying about prime, R mod A is a commutative ring with unity. Okay, so we can prove that part first. Integral domain. Remember the definition of integral domain. Integral domain was a ring that was commutative and has a unity element and had this extra condition about no zero divisors. So before we worry about that last condition about zero divisors, let's just observe that without knowing anything else, just from the setup here, if R is a commutative ring with unity and A is a proper ideal, then R mod A is also a commutative ring with unity. So commutative, that's just verifying that if I have two elements of this factor ring, R plus A times S plus A, the way multiplication works is I multiply the representatives, so RS plus A, but R times S, that's multiplication within the original ring R. So it's commutative, that's S times R plus A, and S times R plus A is the same thing as S plus A times R plus A. So that shows that multiplication in the multiplication in the factor ring is also commutative if the original ring had commutative multiplication. So then what is the unity element of R mod A? Well, it's this. We know that R has a unity element called 1 sub R. If I just take its coset, this will be a multiplicative identity. So I can check, I'll just do one of them. If I multiply this times anything, I'm going to multiply the representatives. 1 times R would be R plus A, so I'd get R plus A as my outcome. So multiplying times 1R plus A, this times this gives me this back. So that tells me this is a unity. There's one very subtle issue, though, that I should mention. So this satisfies the multiplicative identity property, but if you go back, being a unity element is slightly more than that. We need that the unity is not the same as the 0 element. So this will be the unity. Let me give myself some more space, though, to say this. This will be the unity element because it's a multiplicative identity and it's also not the 0 element. And we know it's not the 0 element because of the proper nature of this ideal. If this were the same as the 0 element, that would tell me that 1 so if we assume these were equal, oh boy, we're getting into this. If we assumed these were equal, if we assume that 1 was an element of 0 plus A, then that would tell us that 1 is an element of A. Okay, so two cosets are equal if their representatives are contained in the other. So if 1 was an element of this, that would tell me that 1 was an element of A, because it would be 0 plus an element of A. Well, this is a problem because once something is in the ideal, that element times anything else will also be in the ideal. So any R times 1 would be in the ideal for any R in R. But that tells me any element of R is R times 1. So any element of R is an element of A, so therefore R would be contained in A. But A is already contained in R, so they'd be equal. But we've already said that A is a proper ideal. Okay, so that got a little bit away from me. I forgot about this subtle detail, but we do have to address that because why else do we have to worry about the proper aspect? But finally, we're ready to get to the important part of the proof. We've now shown that just from our assumptions here, in these circumstances, if R is commutative and has a unity, and A is a proper ideal, then this factor ring is automatically commutative with unity. So now all that remains is the extra integral domain property about no zero divisors is equivalent to A being a prime ideal. So let's prove those two directions. Let's do this direction first. We assume A is prime. So it has the property AB is an element of A. It implies A is an element of A or B is an element of A. So now we need to show that R mod A is an integral domain. So we already know it's commutative with unity. We just have that third condition that we have no zero divisors. And if you recall, the simplest way to prove that a ring has no zero divisors is we assume that we have a product in the ring and it equals 0. So now suppose that two elements from R mod A, so that'd be A plus A, capital A, times B plus capital A. Maybe I shouldn't use A and B here. We assume that this equals the 0 element, which would be 0 R plus A. Then what that means is A times B plus A equals 0 plus A. Zero plus A, we can really write that as just A, because it's the set of 0 plus every element of A. Well, any element of A plus 0 is just itself. So this is exactly the set of elements from A, which is A. All right. Now, when we're dealing with equations in factor rings, if a coset equals the ideal, that's equivalent to saying that this representative is an element of the ideal. This is unfortunate. You've got it in front of you, hopefully, so let me just erase. AB plus A equals A. That tells us that AB is an element of A, because it gets absorbed into the A, so it has to already be an element of A. All right, but if A times B is an element of capital A, that means since A is prime, we assumed A was prime, that means one of these two elements is already there. So A is an element of capital A, or B is an element of capital A. But that means that A plus A equals 0 plus A, or B plus A equals 0 plus A. Okay, so remember what we're trying to do here. It's hard for me to keep track because I have to keep erasing. But we were trying to show that the factor ring is an integral domain. So we're trying to prove this no zero divisor property. And so what that was is we're trying to show that if a plus a times b plus a equals the 0 element, which is 0 plus a, we need to show that one of these two factors is already the 0 element. And that's what we've just done. We were able to show by the prime ideal, so since a is prime, we're able to show once we got a, b is an element of a, since a was prime, one of the two elements was already in a, either little a or little b. But if an element's in a, adding the ideal to it just gives you the ideal. It's the same as the 0 element, because an element of a would get absorbed into it by addition. So if a is in a plus a would be a, or 0 plus a. If b is in a, b plus a would be a, or 0 plus a. So either way, one of these original two coset elements was already the 0 element. So this factorization of the 0 element has to involve a 0 in one of the two places. Okay, so that's one direction. So now the other direction, we assume R mod A is an integral domain. I have to just erase it, so I'm not going to write it down. Then it has this no zero divisor property. I'll just cite it when I get to that part. We want to show A is prime. The way to show A is prime is you assume you have a product of two elements that already lives in A. So suppose AB is an element of A. I need to show either little a is in A or a b is in A. So a prime ideal is one where any factorization, any product that's in the ideal already involves a factor which is in the ideal. All right. Then AB plus A is the same as 0 plus A. Because AB plus A, since AB is in A, it gets absorbed into A. But this is the same thing as little a plus capital A times little b plus capital A. So we've come up with a factorization of the 0 element. The 0 element of the factor ring factors as this times this. Now we use the integral domain property. If 0 factors, if the 0 element factors, one of the factors has to be the 0 element. So we have a plus a equals 0 plus a, or b plus a equals 0 plus a. Okay, but here I'm hesitant to erase. If the first happens, if a plus capital A is 0, that tells me that little a is already an element of capital A. If b plus a is 0, that tells me that little b is already an element of capital A. So either way, either a or b is an element of capital A. Let me put that here. A is an element of capital A, or b is an element of capital A. And now we're done. So we assumed that a times b was in A. And we were able to show that that implies either A or B is an element of A. That's the requirement to be a prime ideal. Okay, therefore A is prime. All right. Yeah, so these are getting very definition heavy and abstract, and I'm struggling more and more to teach these to people who aren't here. So I think I'm going to end the video here. Let me just say a few things before I move on. So the key takeaways here, the big thing from this section is the definition of an ideal, being able to, like I said before, being able to prove something is an ideal or is not an ideal. Working with factor rings just a little bit. So understand what a factor ring is, how the operations work, how do you reduce elements in a specific example, especially like a polynomial example. I'm not going to get hung up on definitions like prime ideal, or I guess that was the only one I really did. My goal, I think, is to do one more lecture video over ring homomorphisms. That'll wrap up a lot of this stuff and tie it back to things we did in group theory. Yeah. And I'll put a list of problems from chapter 14 at the end of this video.